Hello everyone, my name is Sian, and I would like to introduce our poster, a novel memory efficient deep learning training framework via error-bounded lossy compression. So to start with, why compress neural networks activation data? Along recent years, neural networks have become deeper and wider, and in general, it's want to have a higher accuracy, and that will introduce a lot of intermediate activation data and hence higher memory consumption. And also limits batch size that we can use when training such neural networks. And in general, larger batch size will result in a higher performance, and also it will make the model easier to be trained. And also nowadays, the GPU memory space is still limited, especially compared to CPUs. So the reason why we can compress such activation data in the training process, we can see in this figure here, the training process with forward and back propagation. In the forward, we are actually save the activation data until the backward propagation, and then the activation data will be reused to compute the gradient and then update the weights. So here, there will actually be a relatively large time period between the activation data being saved in the memory and being reused to calculate the gradient. So what we wanted to do is trying to compress the activation data in memory and then decompress it in the backpropagation when it's needed. And the reason why we concentrate on the convolutional layer is that the convolutional layer is not able to be recompute without a very high overhead. And so the compression will be more suitable. And also it's a large proportion of the activation data consumption during the training process. And in this framework, what we use is the SC lossy compression, that it can provide a very high compression ratio, especially compared to lossless compression. And also it's specifically designed for floating point data, so it's pretty suitable for compressed activation data. And also it's error bounded. That means we can control the error, and we have an error distribution that we can use for our theoretical analysis. We provide a theoretical analysis for error propagation that we injected to the activation data to the overall training performance, and thus we provide the suitable compression configuration for each activation data instead of trial and error, because trial and error is basically impossible to do in neural networks. The training process will take too much time. And thanks to the current work of cuSC, which is a CUDA version of SC, they are GPU-enabled and provide a very high compression and decompression throughput on GPUs. And this is an overall view of our framework. So we can see this is actually a zooming of the previous figure. So with forward and backward propagation on convolutional layers. So what we do is we first collect parameters such as the momentum, average values, and etc. So note here, those dashed line, we will actually only collect those parameters per 1,000 iterations based on our experiment, because those values will not change dramatically, especially after the initial state of the training process. And then we will do the gradient assessment, which we will provide an estimate acceptable error that we can do in the gradient, and then pass it to the activation data assessment, in which part we will provide the error bound for the given convolutional layers activation data. And then last but not least, of course, we will to compress the activation data in the forward propagation and then decompress in the back propagation when it's needed for gradient computation. And we evaluate our framework on multiple neural networks, including AlexNet, VGG16, ResNet18, ResNet50, and all of which result in a fairly high compression ratio on the convolutional layers, up to 13.5 times. And all of which will not affect the accuracy by much. And here on the left side, we can see this is a comparison between the original training curve and our compressed model training curve. So you can see they aligned pretty well with each other. And also this orange line here is actually the compression ratio along different iterations. So we can see our framework also provide a relatively stable compression ratio along different epochs. And in terms of the performance or the overhead of our framework, thanks to the high compression and the decompression throughput of cuSC, we actually introduce a relatively low overhead, as low as 7% of the total compute time. And also because we save the memory consumption, so we can increase the batch size, and that will increase the performance by up to 1.27 times raw performance, that is image per second on GPUs, because larger batch size will make the GPU compute more efficient. And also there is other potential improvement based on the larger batch size, for example, the larger convergence speed, and also the model will be easier to train with larger batch size. So in general, in conclusion, our proposed framework is a novel memory efficient training framework via dynamically compressing the intermediate activation data through error-bound lossy compression. And we provide a theoretical analysis of the error propagation during the training process. And based on that, we provide an adaptive scheme to dynamically configure the error-bounded lossy compression based on a series of current training status data. And we evaluate our proposed framework on multiple popular models and provide a very decent result. So some of the future works include that we want to experiment how to implement orthogonal methods, including like data migration or data recomputation to our framework to see if we can further improve the performance. And also we would like to try to optimize the performance on the activation data. For example, the compression and decompression overlay we can do for the computation. And that's all. Thank you.